Hello, and welcome to part 21 of the packaging series. My name is William Mitchell, and today we're going to be talking about the packaging substrate. The material in this video is brought to you by work done in the University of Florida's SCAN lab under the supervision of Chengji Ji and Dr. Naveed Asadi. The purpose of this video is to discuss packaging substrates and explore the innovations that have developed over the past few decades. We'll start with an introduction to the packaging substrate and differentiate it from the iconic silicon interposer and the common printed circuit board. Once we establish a basic understanding of substrates for packaging, we'll explore how engineering substrate materials is key to unlocking their potential. And this covers ceramic, organic, and glass substrates, along with the possibilities of integrating passives and embedding bridges. For packaging purposes, the substrate acts as a carrier for the die, spreading underneath. It's an abstract concept when it comes to packaging because the substrate can fill many roles and has been reinvented several times. The primary function is to form electrical interconnections between a die and external functional components like passive devices and other packaged chips on a printed circuit board. Secondary benefits include improved mechanical and thermal stability, and material choices can enable enhanced electrical performance. Now, traditionally, the substrate was known as the silicon wafer, where devices are patterned and diced into chips to be packaged and mounted on a PCB. When it comes to packaging, the substrate acts as an intermediary layer that routes the nanometer-sized interconnections from the die and scales them so they can be mounted on a PCB with human hands. What you may be familiar with is the silicon interposer, which uses a redistribution layer and through silicon vias to route interconnections between chips and the packaging substrate. The benefit of using a silicon interposer is to avoid passing electrical signals through a matrix material other than silicon when communicating between chips. Depending on the material, the packaging substrate can have worse electrical properties than silicon, and passing signals through can result in loss and decreased performance. An easy solution is to work with the familiar material, silicon. And by design, the function of the silicon interposer is essentially the same as the packaging substrate. We have conductive horizontal routing layers and vertical through vias to network interconnections between two mediums. One could say that the silicon interposer functions as an additional packaging substrate. And in the same way that the silicon interposer can be considered a substrate, the substrate can be considered a miniature printed circuit board, where both serve as platforms for mounting and interconnecting electronic components. They both route electrical signals from one place to another. The major difference is that the packaging substrate only provides interconnections within the packaged device, where the printed circuit board creates a network of large-scale components like resistors and capacitors and typically other packaged devices. When it comes to materials, the printed circuit board is almost always epoxy composite with copper traces. And on the other hand, the packaging substrate is more of a mystery. The material choice is highly dependent on the application, and there's lots of ongoing research to further optimize those design choices. In just the past few decades, the dominant substrate technology has evolved from ceramic to organic with embedded bridges, and now the next generation of substrates, which includes the glass substrate. The reason for this development of substrate technology is the same quintessential demand for smaller, more powerful computers and the desire to fit more transistors in a single area. The trend towards smaller devices has been enabled over time by 3D packaging. Technology like the flip chip ball grid array, system in package, and 3D integrated die stacks are pushing the limits of device performance, and the hidden element enabling these is the advanced packaging substrate. The early ball grid array was enabled by a ceramic substrate, and then material innovations made organic substrates more appealing for manufacturers. And today, with artificial intelligence applications and the massive amounts of data being processed by industries, the popular organic substrate just can't quite keep up. Some applications need something better, and to meet the growing demands, the answer is to look deeper at the packaging substrate. We'll start with ceramic substrates, which may not be the most popular option nowadays, but certainly have their place as the most robust option. Known for their high bond strength, these covalently bonded ceramic materials bring a lot of dimensional stability to the package and can provide reliability in extreme conditions. Ceramic substrates also typically have a higher thermal conductivity than organic substrates, making them ideal for managing thermal properties in high-performance computing where joule heating can hinder performance. The dimensional stability of ceramics allow more design freedom when it comes to processing temperatures, and achievable ultra-low flatness can significantly improve lithography steps. Common materials you may see as ceramic packaging substrates include alumina, aluminum nitride, silicon nitride, or beryllium oxide for high power and high frequency applications. Now, a more important quality for ceramic substrates is that they have a coefficient of thermal expansion that's well matched to silicon, meaning that thermal fluctuations are less likely to damage interconnections between the silicon die and ceramic substrate. And since the coefficient of thermal expansion is less than the PCB, when you design a ceramic substrate, you must keep in mind that the size of the package will affect the stress placed on the interconnections between the packaged substrate and the printed circuit board. An example ceramic substrate concept that's being researched is the diamond substrate, which hyper-focuses on maximizing thermal properties. That's because in advanced high-density packages, joule heating can become a major problem. When these chips are stacked vertically, lots of heat is generated by the finite resistivity of the conductive pathways, and this heat can cause a lot of problems for device performance, scattering signals, and reducing efficiency. If the priority is to manage heat, the best choice for a packaging substrate would be one with a high thermal conductivity, so that it can efficiently distribute heat away from chips and toward a heat sink. Since diamond has the highest thermal conductivity, it could be an ideal choice. It has a wide bandgap, making it electrically insulating and allowing for a high density of isolated interconnect vias. It also has a very high mechanical strength, just like other ceramic substrates, making it very robust. The major downside to using diamond as a packaging substrate material is simply the cost and manufacturing challenges. Until synthetic diamonds can be reliably grown cheap and easy, there are simply other choices that are more cost-effective and have a more well-rounded set of properties suited for a packaging substrate. Organic substrates offer a cost-effective option for packaging substrates while maintaining good material properties. A major reason organic substrates became so popular is that they could take advantage of the already optimized, low-cost PCB manufacturing technology and infrastructure. The early organic substrates were even considered smaller and simpler versions of PCBs, but for packaging. They kicked out ceramic substrates as the primary option, and now organics are widely used, while ceramics are reserved for when high reliability and performance are non-negotiable. Common materials for organic packaging substrates are FR4, a common PCB composite, liquid crystal polymer, or Teflon-based composites. And an important quality of organic substrates is that their coefficient of thermal expansion is well matched to the PCB. This means that the interconnections between the substrate and the PCB will be less affected by thermal fluctuations. And since the coefficient of thermal expansion is much greater than the silicon die, the size of the silicon die will be the factor driving interconnect stress between the die and the substrate. Now, although organic substrates are well suited for mass production, they are limited by their thermal performance and susceptibility to harsh environments and high processing temperatures. The Hyper-BGA is an example of an engineered organic substrate using a Teflon-based composite with silica filler. The use of Teflon provides a low dielectric constant that leads to low loss, enabling extremely high signal speeds but requiring more passivation. And the silica filler is implemented to decrease the coefficient of thermal expansion of the organic Teflon to be in between that of the silicon die and PCB. And to combat the mechanical instability, a ground plane of copper-clad invar, or a layer of copper surrounded by a nickel-iron alloy, is placed at the center of the substrate. The copper-clad invar center plane provides extra dimensional and mechanical stability, and its low coefficient of thermal expansion helps reduce the overall thermal expansion of the package. And the Teflon laminate that surrounds the center plane provides those desired material properties for the substrate matrix and a little extra compliance to distribute stresses throughout the package. Overall, the Hyper-BGA is a commercial design for an organic packaging substrate that uses clever material combinations to reduce size, weight, and consumed power. In pursuit of an even better packaging substrate solution, major semiconductor players like Intel have been researching and developing the glass substrate for over a decade as an inorganic and amorphous replacement for the popular organic substrate. The glass substrate possesses extremely desirable electrical and optical properties, is chemically inert, and is highly resistant to moisture. Its low dielectric constant makes it more difficult to isolate conductive interconnects, but greatly improves signal integrity, and the coefficient of thermal expansion is perfectly matched to silicon. That's because most glasses are silicon-based, with other additives hidden behind proprietary brand names such as lithosil or borofloat. The most common benefit of glass substrates is the ultra-low flatness, which improves the depth of field for lithography, allowing feature sizes to be reduced. And along with the tolerance to high processing temperatures that provide design flexibility and superior dimensional stability, glass substrates have been shown to provide up to 10 times the interconnect density of organics. The catch is that this technology is still in its infancy, and the cost and yield challenges associated with manufacturing glass substrates have yet to be overcome for commercial production. The future is exciting though, and Intel isn't the only company with their eye on the glass substrate. With more development of infrastructure, it's likely that we will see glass substrates enabling machine learning and high-performance computing applications in the coming years. Research from 2010 has already shown the competitive nature of glass substrates with organic-based packaging. GlassPack is a novel system-in-package approach investigating the glass substrate for electronic and photonic applications. The high dimensional stability of the glass substrate allows the integration of actives, passives, and optoelectronic components that transform electrical signals to optical signals. And this is necessary in high-speed data communication when electrical signals in the gigahertz frequency range must be transformed into optical signals, and is done by integrating lasers and photodiodes into the package. Mirrors and optical waveguides route the signal through the substrate and interpret between optical and electrical waves. A drawback of the glass substrate is that it has a low thermal conductivity and cannot efficiently manage the heat generated from the lasers and joule heating from electrical signals. Some metallization can help manage the heat by providing thermally conductive pathways towards heat sinks, and future innovations in glass materials can help solve this issue by improving the thermal conductivity. Another drawback of the glass substrate is that it's difficult to realize these high aspect ratio through glass vias for routing signals vertically, but manufacturing techniques for glass substrates have yet to be optimized, and further research may discover better etching methods to help realize these high aspect ratio vias. When the packaging substrate has a high dimensional stability like ceramic or glass, passive devices that would normally take up valuable space on a printed circuit board can be integrated into the substrate. These are passive devices like resistors, capacitors, and inductors that could sometimes be half the size of the chip itself. The main challenge is achieving a device on a chip scale that performs close to its normal-sized counterpart. And the size sets dimensional limits on the achievable electrical properties, and precise details increase the minimum achievable tolerance to above 10%, which isn't very great. For resistors, the thin film resistor was adapted where length and resistivity are maximized. You can see this in the meander type resistor, which aims to maximize the length of the resistive pathway. For capacitors, thin film capacitors were adapted where thickness is minimized and area and permittivity are maximized. Inductors are much more challenging to realize on a chip scale, so only applications with low inductance can be effectively realized within a substrate. Now that we've discussed integrated passive devices, we can talk about more complex passive devices like silicon bridges, which are embedded conductive traces forming interconnections between chips in 2D space. This technology enables interconnects for multi-die packages like system-in-package. and in its simplest form, the silicon bridge can be fabricated into a silicon interposer along with other conductive routing layers. Maintaining the silicon matrix around the conductive traces protects the signal's integrity and provides the shortest path possible to communicate high-speed data. And adding an additional interposer layer above the packaging substrate can be pretty expensive though. So an alternative is to cut out the silicon bridge and embed it within the package substrate itself. This approach maintains the signal integrity and short path length of interconnects when using the silicon interposer without needing the entire layer. But as you could imagine, the implementation of the silicon bridge can be very difficult. Mounting and aligning chips adds yet another step in the packaging process and can severely inhibit yield. Despite the challenges though, silicon bridges are an innovative approach that can be extremely powerful in enabling multi-die packages, even if the method isn't commercially viable yet. The research and development is necessary though, and I hope learning about the packaging substrate today gave you a new perspective on the innovations happening in the semiconductor world that enable the technology of the future. It'll be really exciting to see where the next advancement in substrates can take us in terms of pushing the limits of what's possible with computers. If you would like to explore further on the topics discussed in this video, the sources listed in the bottom left of each slide are referenced here.